Morning, everyone. Sorry I am not there today. I'm going to go ahead and teach this as if I am. Um, right, so the write up for Mechanics 1 Part 2, which is the acceleration one, is due today. So if you have it, give it up there and leave it on the desk in the lab. If you don't, I will take it on Thursday for correction. If it's not there on Thursday, negative points. Your proof test is on Thursday. So one proof on Thursday. All right. Right. So this was the third thing I asked you to do for homework, which was about velocity time graphs, because that's what we were doing in class on Friday. So a lorry is travelling in a particular direction along a road. Figure 7.8 is a graph of its velocity plotted against time. From the graph, find the velocity of the lorry after 4.5 seconds. So 4.5 seconds is a time. So I'm going to do it on here because it's less jumpy. I go to 4.5 seconds, see where the cursor is here on the time axis. Sorry. Let's not do that with a highlighter. We use a pen, actually blue. So, right, try that again. So go to 4.5 seconds here. Go up. Looks about right. Until I hit the graph. And then take it from there across. Yeah. So that looks around 7.5 to me. So like that point there would be 7. So maybe 7.4. Actually, it doesn't quite look halfway. So let's go 7.4. So I'm going to say the velocity is 7.4 meters per second. Okay. The time taken for the lorry to reach 7 meters per second. So same question, except that this time they've given me the velocity and they want me to find the time. So I'm going to go to 7 because that's what they're asking me here. Here. So I'm going to go to where I put that dot. I'm going to go across till I hit the graph. And then I'm going to go straight down from there, which looks to me to be bang on 4 seconds. So that is a time equal to 4 seconds. Okay, the acceleration of the lorry. So this is a velocity time graph. So to get acceleration, we need to do v minus u over t, which means we need to do velocities over time. And to use this graph, because it does say up here, from the graph, find this. We have to use the graph. So to use the graph to do this, I need to put the velocity over time, which is the y-axis over the x-axis. Yeah? And the y-axis over the x-axis is rise over run. And rise over run is slip. Okay, so it's a really long-winded way of saying if you want the acceleration, you need to calculate the slip. Okay, so I'm going to go back over here. I might do this in yellow. I'm I'm going to actually go right. You need to pick like points where you're very, very clear where the start is and very, very clear where the end is. So I think I'm just going to go to the start and the end. It's just easier. So let's see. We'll go yellow. And I'm just going to draw a line this time. So I'm going to go across there. And then I'm going to put in another one. And I'm going to go down that way. Okay. So this one up here is my y values, which is my rise. And it starts at 4. Yeah, to get that 4, I'm looking like across this way. And it goes up to 10. So 10 minus 4 is 6 for the rise. And then for the run, I'll just do it in pink. So the run, we're looking down the way. Yeah, so that's 0. And then over here, it's 8. So to get the run, I should have said we're going to use the x values. And the x values give me 8 minus 0, which is 8. Yeah? So if I go back over here, to get my acceleration, I'm going to put the y values over the x values, which is the 6 over the 8, which is 0.75 meters per second squared, because it's an acceleration. Yeah? Okay, and the last one is the distance travelled by the lorry in 5 seconds. So now I was a little bit rushed doing this on Friday. So to get the distance travelled from a velocity time graph, we need to get the area under the line. Okay. So the distance travelled by the lorry in 5 seconds. I'm going to clear off. You've seen how I got all of these. So I'm just going to clear off all this information. Okay, so the distance travelled by the lorry in 5 seconds. So that makes 5 seconds. Draw. Let's do black. Insert. I'm going to insert a line. I'm going to go to 5 seconds and draw that. Yeah? So, now I'll get rid of this now, but to get the distance travelled by the lorry in 5 seconds, I need to figure out this area. Yeah? Now, same as what we were talking about the other day, that's not an area that, that's not a shape that we know. So what we do is we split it up and turn it into a shape that we know. So the bottom bit down here is a rectangle, and the top bit up here is a triangle. Yeah? So to get the rectangle, we do length by width. And the length of that rectangle is 5. And the width of it is 4. Yeah, can you see that? So along the bottom line here, that's 5. And up the side here is 4. So 5 times 4, that's 20. Yeah? And then the triangle is half the base multiplied by the height. So half. Now the base is going to be the same. Base is going to be 5. It's half the base. Multiplied by, now this height is a little bit tricky. So it starts here at 4 and it goes up to like here. it's not quite 8, like that's like 7.9. I mean, I kind of have to read the graph as it is. So I think the height is 3.9. It goes from 4 to 7.9, so 3.9. So if I do 3.9 multiplied by 5 multiplied by a half, I'm getting 9.75. Did I do that right? Yeah, 9.75. So then add them together, 9.75 plus 20, and you get 29.75 meters is the distance travelled in 5 seconds. All right, so that's using a velocity time graph. That was your homework. So now I just want to move on to this. So the first part of this chapter has been about horizontal acceleration, so like a car or like a train or whatever, and it's traveling along and then it increases its speed over a period of time, or it's at rest and it increases its speed. So what we're talking about here now with acceleration due to gravity is we're talking about vertical acceleration. Okay, so we're either talking about an object that is being dropped, which means it's going to, it's going to pick up speed. Or if you have an object that is in your hand or whatever and you throw it up, then as it goes up, it's going to lose speed. Okay? And remember, if the speed of an object is changing or the velocity of an object is changing, then in both of those situations, the object is accelerating. So what we're talking about is the acceleration So we're looking at the acceleration that is caused by the force of gravity. Okay, so that's what we're looking at. We're looking at the acceleration that's caused by the force of gravity. If you're dropping something, then that something's going to be kind of picked up by the gravity and accelerated. And if you're throwing something against gravity, then gravity is going to slow it down. Either way, its speed or its velocity is changing. And if its velocity is changing, then it is accelerating. Yeah? So I did, with the transit, any of you that were in transition year last year, we did talk about this last year. So if you drop an object, so in this little picture here, okay, so here we have like a coin, and then over here we have a feather. All right, and as an object is dropped, gravity accelerates that object towards the surface of the earth. So both the coin and the feather will experience a gravitational force on them, pulling them towards the center of the earth. But they will not fall and hit the ground together. Okay, so if I draw the coin here outside and I draw the feather here outside, the force of gravity acting on both of them is going to be exactly the same, okay? Because the force of gravity depends on where they are, and they're both being dropped from, I don't know, my hand standing in the lab. So the force of gravity acting on both of them is going to be identical, because the force of gravity only changes if you go really, really far away from the surface of the earth. So like if we go to the moon, the force of gravity is different. All right, but anywhere in the surface of the earth, the force of gravity is the same. So you have the same force of gravity acting on the coin and the feather. So the question you should be asking yourself is, well, if they have the exact same downward force acting on them, why don't they hit the ground together? The reason they don't hit the ground together is because of air resistance. Okay, so when you drop the coin and the feather, the downward force is exactly the same, but the upward force is completely different. The upward force acting on them is air resistance, and the coin is much more aerodynamic, so the coin can cut through the air much better than the feather can. The shape of the feather, the mass of the feather makes it perfect to be picked up by the air and sort of floated down. Okay, so to see the true effects of gravity, you need to drop the coin and the feather in a situation where there is no air. Because if you can take the air out of it, if you can take this bit out of it, then you'll be able to see the fact that the gravitational pull on both of them is identical. Okay, and that's what's going on in the second one. If you look down the bottom of the second tube there, that tube is a vacuum, which means they've removed the air, and you can see the coin and the feather together. Okay, I'm going to put a link in to the OneNote. So, sorry, there is a link in the OneNote just below this paragraph. I want you to watch that. Now, we did watch it in TY last year, but I really need you to watch it again. So what you're seeing is just an experiment showing exactly this. Okay, there's a bowling ball and a feather being dropped. They both get dropped. They're both right beside each other, so the same gravity is acting on both of them. But they do not fall and hit the ground together because the feather is much more heavily affected by the upward force of air resistance than the bowling ball is. But they are in a scenario where they can move. They do it in NASA, so they can remove the air and create a vacuum. So now those upward forces just aren't acting. And you can see that in the absence of those upward forces, the only force on them is gravity, and they do in fact fall together. Okay, so you can see the true effects of gravity. So I want you to watch that video now. Just follow the link. So just very briefly to talk about the value. Have we used it already? It must have been last year. So gravity anywhere near the surface of the Earth is around 9.8. It's an acceleration, so 9.8 meters per second squared. Now, you can see here, and we will talk about this when we're doing, I can't remember what chapter it comes up in. I'm not sure. Pressure gravity moments. So when we're actually talking about gravity, we talk about how it's not exactly the same all over the Earth, and it's to do with the shape of the Earth. So as you move further away from the center of the Earth, the gravity does change slightly. So you can see here at the top of Mount Everest, it's a little bit lower than it is in London, for example. Okay, so I don't want to get into this too much here, but it's because the Earth is not a perfect sphere. You do have parts of the Earth where you're a little bit further away from the center than in other parts. So the North and South Pole are actually a little bit closer to the center of the Earth than the equator. Okay, because the Earth is like, if you imagine a sphere and then put your hand on the North and South Pole and squish it a little. And so that's why gravity is ever so slightly different. But to one decimal place, anywhere on the surface of the Earth, it's 9.8 meters per second squared. So we use that number quite a bit. Okay, now I'm just going to do one of these because there's not a whole lot of difference between the ones we did last time and these ones. And this is using the equations of motion. So our equations of motion are V equals U plus AT, V squared equals U squared plus 2AS, and S equals UT plus a half AT squared. But this time we're talking about vertical accelerations. Okay, so an object is dropped from the top of a building, which is 30 meters high. With what speed does the object hit the ground, and how long does it take to reach the ground? Okay, so I'm going to put down my UVAST, U-V-A-S-T. So do I have an initial velocity or an initial speed? It says the object is dropped, which means someone or something is holding it. So its initial speed is rest, which means 0. From the top of a building, which is 30 meters high. So 30 meters is a height, which is just a vertical distance. So that's going to be S. And the units are correct, 30 meters. So that's fine. We don't need to mess around with that in any way. Now, if it's being dropped, we know the acceleration. Okay, if something is dropped, then it's going to fall under the force of gravity. So that means our acceleration is going to be 9.8. So I can put that in. And with what speed does the object hit the ground? So we're looking for this. With what speed does the object hit the ground? Okay, there's a second question, but we'll deal with this one first. Okay, so you pick your formula that's going to work. And for u, v, a, and s, it's going to be the second one. So v squared equals u squared plus 2as. V we don't know, so leave it as v. U is 0. 2 is 2. A is 9.8 and S is 30. There's no rearranging required because the V is already isolated, so I can just type the right hand side into my calculator and I get 588. And then to get rid of the square, because I don't want V squared, I want V. So to get rid of the square, I'm going to need to do a square root. Sorry, I'm just waiting on the laptop to catch up. There you go. So I'm going to need to do a square root, which will cancel my square. And I get 24.25 meters per second. That's rounded to 2 decimal places. And then the second part of the question there is how long does it take to reach the ground? So that's a time. Yeah. Time isn't isolated in either equation, so I'm going to go with the top one, v equals u plus at. So v equals u plus at. V is 24.25. U is 0. A is still 9.8. And then T is T. So 0 plus 9.8T is just 9.8T. And then to isolate the T, I'm going to have to divide by 9.8 because the T is being multiplied by 9.8 at the moment, and I want that multiplied by 9.8 to go away. So I do that with a divided by 9.8. But you can't divide on the right unless you divide on the left. So 24.25 divided by 9.8 is 2.47 seconds. So that's it. Like I said, same formulas, same method. Write down UVAST and then sub in what you know. And the only difference here is that your acceleration, if the thing is dropping, whatever the thing is, if it's dropping, it is plus 9.8. If you're throwing something up, so it's moving against gravity, then that thing is going to be decelerating, and that would be minus 9.8. That's it. Everything else is going to be the same. Yeah? So, there is a kind of proper higher level question here where it does both acceleration and deceleration, but I'm not going to give you those today because I want to do those with you. So let's have a look at... Okay, so we'll go... I'm going to do 2, 3, 4. Yeah. Okay, 5 is a little bit more challenging, but I think you should be okay. Okay, so 2, 3, 4, and 5 is going to be your homework. So I'm going to pop them back in here. What's that, the 4th? Sorry, I don't know why it's a bit funny. Oh, actually, sorry. I'm going to start a new one. Now, okay, so that is your homework. And that is due for Thursday, along with these bits. Your mandatory experiment write-up if you haven't handed it up, and please be prepared for your proof test. Is that okay? Grand. So I will see you Thursday.